Hey, let's talk about normal distributions. Okay. So you've definitely heard about distributions before, but you've heard about them as probability distributions, right? You were like, okay, I've got the desired outcome X, right? And then I have the probability of X occurring. So let's say we had a four-sided die and we rolled it. The outcomes are 1, 2, 3, and 4. The probability of each outcome occurring is 1/4 because it's a four-sided die, whatever. So if you'll notice, these desired outcomes are whole counting numbers or integers. Those are called discrete numbers or counting numbers. Okay. When you're examining data that's discrete, it's whole numbers, right? It's like number of owls in a forest, number of dice sitting on a table, number of green marbles in a bag. Okay. Those are called discrete data. Now, what if you're analyzing data that can be any numerical value, aka continuous? So let's say I wanted to examine the heights of all the children in the Hilton Central School District. I would probably want to start examining the little kids first. Their heights are probably the lowest is going to be like 3 feet tall. And then I'll get to the older kids, and their height is probably going to be at the highest 6 feet tall. And then if you asked me, it would be even taller than that now. But basically, these are usually things that are measured, like continuous data are usually measured, such as height, length, time, and speed. And whatever data you come up with is usually in a range of numbers, right? It's an interval of numbers. So continuous random variables can take on all different kinds of shapes of distribution, and you'll learn about all the different shapes of distribution when you go to AP Stats or in college. But the one that we will be focusing on today in this class is the normal distribution, and you've totally heard of it before. It's called the bell curve. Boop. So it is given by a function of the form f of x is equal to 1 over the standard deviation of the square root of 2 pi times e raised to the negative 1/2. And then in parentheses, we have x minus mu over theta squared. So if you'll notice, the shape of this bell curve over here is going to depend upon the standard deviation and the mean. And this equation basically represents a family of functions that depend on the mean and the standard deviation. And then inside of this family is, so like the overarching like parent is going to be like the normal distribution. Let's think of him like the parent. And then he has one very special child, the standard normal distribution. So while the parent normal distribution, right, he's going to depend upon your mean. He's going to depend upon your standard deviation. The standard normal distribution is a special kid where his mean is always going to be 0 and his standard deviation is always going to be 1. We'll talk more about him in class and why he's special and what we can do with him. But right now, just know that he exists as a member of this family of functions. So the probabilities for a normal distribution all add up to 1. And here's why. When you were looking at probability distributions back when you were super young in October, you found that if you added this bottom row together, all the probabilities added up equal 1. Well, in this family of functions here that generate the normal distribution, if we were to find the area under the curve, so some statisticians kind of crunched these numbers and they were like, yo, if we took the integral of this guy and we found the area under the curve, because that's what an integral does, it finds the area under the curve, we would find that all of those probabilities add up to 1. That's super cool, man, right? So they would find that out and they would be like, dang, that makes perfect sense because in this type of probability distribution, all the probabilities add up to 1. And in this type of probability distribution, all the probabilities add up to 1. Cool. Do you need to know this? No, but I thought you might want to know a little bit of the why behind it because I feel like when I was in college and I was learning about these, I was like, all right, these are cool, but like what actually is a normal curve? Where does it come from? It is a member of this family of functions. Okay. So the standard normal distribution has a few cool special features, right? This is the mean. Within one standard deviation of the mean, we have 68% of the data. Within two standard deviations of the mean, we have 95% of the data. And then within three standard deviations of the mean, we have 99.7% of the data. The actual normal curve itself is asymptotic to the x-axis, which will be useful later when we are trying to generate the upper and lower bounds for our normal CDFs and inverse norms. And the total area under the curve is equal to 1. I think we talked about that already. And the standard deviation is kind of what dictates the shape of the bell curve, right? So if everything is gathered nicely around the mean, he looks like this. And then if the data is gathered super close around the mean, he's going to have some tall little spike there. If the data is super spread out, the standard deviation is high and the graph is a low bell. All right, let's talk some more in the sense of examples. So how are you going to use normal distributions? So if we are given the bounds, right, we can use a special function on our calculator to calculate the area under the curve between those special bounds. So I'm going to read this problem. X is normally distributed with a mean of 70 and a standard deviation of 4. We want to find the probability that an X value falls in this area on the graph. So if you'll notice, the area here is unknown. Area, unknown. When we have an unknown area and we're trying to find the area or the probability, we are going to use something in our calculator called the normal CDF, okay? And inputs for the normal CDF are going to look like this. So it'll look like normal CDF, and then we would enter menu 552, and we're going to look at our graph. The lower bound is a 60, the upper bound is a 72. Maybe if we think about these like test scores, it'll kind of help us like contextualize the problem, right? The mean is 70 and the standard deviation is 4. So my calculator spits out a probability or an area under the curve bounded between 60 and 72 as 0.685. So the probability that a score fits within that percentage is 685, or fits in between these two scores is 0.685. Now let's find the probability that a score is, why are these all gross? Okay, there we go. Let's find the probability that a score is greater than 76. Well, we're still using the same mean. So now we're above the mean, same standard deviation. And we're looking for greater than 76. That means we're looking for this area under the curve right here. Since we're looking for an unknown area, we're going to use normal CDF. And let's talk about our inputs. Menu 552. So our lower bound is the score of 76. Our upper bound, remember we talked about how the normal curve is asymptotic with the x-axis. Our upper bound is going to be infinity. And the way that I always put that in the calculator is just 9 times 10 to the power of 99. That's what that button EE means, to the power of, times 10 to the power of. So our mean here is 70. Our standard deviation here is 4. Hit OK. Boom. 0.067. 0.067. So the probability that we get a score greater than 76 is 0.067. All right, cool. Let's look at some other problems that we have. So here, example 2, X is normally distributed with a mean of 32 and the standard deviation of 3. We've got our curve that looks like this, mean of 32, standard deviation of 3. We're trying to find the value of K such that the probability that x is less than k is 0.37. Oh, wait, my picture doesn't make a whole lot of sense, right? The probability to the left of k is only 0.37. He must be below the mean. So let's put him over here. Okay, so such that the probability of x is less than k is equal to 0.37. So let's put him on here. Hello. What's the difference between this problem and then problem up top? In this problem, we are given the area, or we can say that the area is known. When we have a known area, we're going to use something called inverse norm. Okay, and I'll show you the inputs for inverse norm. The area to the left of, that's going to be a bad color. The area to the left of k is 0.37. Let's look at what we would do here. So we use the normal CDF function on our calculator when we're trying to find the area or probability, or when the area is unknown. But when we're given the probability or percentage of values for a normally distributed random variable, we can find the particular value, or k, that gives that probability using the inverse of the normal distribution. That's the inverse norm thing that I was just talking about. So on your calculator, that looks like inverse norm. We do menu 5, 5, 3. And then it asks us for that area that it was talking about in the problem, 0.37. We have our mean of 32, and we have our standard deviation of 3. And our calculator will tell us what that k value is. Sweet. Okay, so when k is 31, yeah, pretty much we can leave it at 31. When k is 31, the probability that x is less than k is going to be 0.37. Cool. So the inverse norm function on your calculator, right? It only calculates the area, or like the cumulative area from the left. So if you draw a standard bell curve and you've got this part of your graph shaded, you're good. But if you are given a probability from the right, you are going to have to find the complement, because your calculator only finds cumulative probabilities from the left. Okay. What am I talking about? Who knows? Let's read this problem and I'll show you what I mean. So scores on a physics exam are normally distributed with a mean of 76 and a standard deviation of 5. Okay, so we have mean is 76, standard deviation is 5. The teacher decides to award an A to the top 7% of students. Find the minimum score required to earn an A. Okay, so this teacher was like, all right, we got the top 7%, right? They gave you the percent, or the area under the curve. We know that the top 7% of students have a score that lies in this part of the standard bell curve. We are trying to find this cutoff point, this K, that would make the kids have an A, right? This is the minimum score required to earn an A. So this is exactly what I was talking about before, where like they didn't give me the probability on this side. I need to find the complement by subtracting the probability on the right. So 1 minus given, and that will give me the probability on the left. So the probability on the left is 0.93. And now that I have that, I can stop. And now that I have that, I can use my calculator to calculate that K value that I'm looking for. So we've got menu 5, 5, 3 for inverse norm. Our area to the left is 0.93. Our mean is going to be 76, and our standard deviation is 5. All right, so kids got to get an 83. Kids got to get an 83. Oh my gosh, I'm trying to like write this thing at the same time. Here we go. Kids get an 83.379, and that earns them an A. What do you mean an 83 is an A? Well, this is what happens in college a lot, right? When like professors curve a big exam because everyone did super cruddy, this is what they mean, right? Now all the values of K are going to be like curved to an A. All right. Cool. All right, so why did I include this big scary table here? So the inverse of the normal distribution can also be used in problems where we know probabilities, but the mu and the standard deviation are unknown. So to do this, we must first convert the x values to z-scores using the formula z is equal to x minus mu over the standard deviation. This is known as standardizing. So remember before, like how we talked about how like we talked about normal distributions as a family of functions. Well, there is a very special member of that family known as the standard normal distribution, and we learned all about him up top. His mean is 0. His standard deviation is 1. Every score in a normally distributed data set has an equivalent score in the standard normal distribution, right? So if you took, where's my picture from above? If you took like a score here and you kind of converted it over to the standard normal distribution, that's what's happening when you are like standardizing a z-score. Okay. Every score in a normally distributed data set has an equivalent score in the standard normal distribution, and that is why z-scores work. This means that the standard normal distribution can be used to calculate the exact percentage of scores between any 2 points on the normal curve. So statisticians have worked out tables for the standard normal curve that give the percentage of scores between any 2 points. And in order to be able to use this table, scores need to be converted into z-scores. So like when I was in college, we had to learn how to use this table by hand to deepen our understanding. And like, yeah, we use the calculator too, but like we had to learn it this way first. And I do believe there is some utility in that. So I'm going to show it to you just to see where z-scores come from. But then just know that like when your calculator spits out a probability for a certain area of the graph, it comes from z-scores. So when we're looking at the z-scores, right, these are all negative because they're basically just saying like, hey, we're just going to give you the z-scores on the left, right? Negative 3.4 would be somewhere way out here. And then like negative 1.4 would be like kind of close to the mean. And then like negative 0.0 would be like right over here, right at the mean. Okay, the z-score of 0 is going to be the mean. But it's basically saying like where a data point is located in relation to the mean. The reason why these are all negative is because like they just kind of gave you the negative side, and then we're like, this is symmetric, so just go ahead and like double mirror image it on the other side for everything that's a positive z-score. So like, let's say you were looking for the area under the curve for a z-score of negative 6.15. So you input your x, you input your mu, you input your standard deviation, and you got a z-score of negative 1.65. So you would go over to the table, right, and you would look for negative 1.6, and then you would go to, this is like the hundredths. These are like the hundredth place columns, right? So you would like go down until you hit over here, and then that would correspond to an area under the curve of, so like you have like negative 1.65, here's your mean, and the area under the curve to the left of that would be 0.0495. So like, I don't know, statisticians made this table, your calculator just spits out the area for you, but like here's where those areas come from. Boom. Z-scores describe the exact location of every score in a distribution. So, for example, whether the score is above or below the mean, right? The z-score is going to be negative when the score is below the mean. A z-score is going to be positive when it's above the mean. The mean has a z-score of 0. And the z-score is the distance between the score and the mean in terms of the process. Oh, in terms of the number of standard deviations. I mean, like, look at the formula. That's exactly what it says, right? It's like you're finding the difference between your x value and the mean. You're dividing it by the number of standard deviations, and that gives you your z-score. That tells you where that score falls in term or in relation to the mean. So the whole process of converting x values into z values is known as standardization. And we're going to do one quick example before you fall asleep in your bowl of popcorn or whatever it is that you're eating. I know this is long. Sorry. Love you lots. Okay. So x is normally distributed with a standard deviation of 22. given the probability that x is less than 40 is 0.12. Wait, why did I first initially go to draw the line here and then change it? Because a probability of 0.12 is going to be super close to the left part of the graph because it's a tiny probability. So I changed that and we got 0.12. The mean is unknown, but we do know that this guy is 40, right? So since the mean is unknown, first we must standardize the x value, which in this problem is 40. So we have the probability that x is less than 40 is equal to 0.12. He is now going to be 0.12 is our area to the left of the curve. And we have 40 minus mu over 22. That gives us our right-hand side, right? We're plugging in the formula z is equal to x minus mu over the standard deviation. So now we can use the inverse normal button to see what that area of 0.12 corresponds to on the normal curve, where the mean is 0 and the standard deviation is 1. Okay, this helps us to solve for our unknown of mu. So you standardize with one on one side with the z-score, standardize on the other side with the inverse norm and the standard normal distribution. All right, so we've got the inverse norm let's type that in menu 5, 5, 3. The area is 0.12. And look, this is used all the time. The standard normal distribution is used all the time to help solve these. So like it automatically defaults to a mu of 0 or a mean of 0 and a standard deviation of 1. So you go ahead and hit that. And now you have your z-score. All right, cool. So now you would just solve for mu or the mean, and you would get 65.8. So the mean here is 65.8. If any of this was too fast, that's okay. We're going to do tons of examples in class. I just wanted to give you like a huge overview of what is actually occurring.